Okay, well, hello, welcome back to the fourth of 5 sessions and our Knowledge Zone offering for 2024. I'm really going to enjoy today. I got handed this bar of chocolate yesterday. It still has 92% cocoa or cacao, doesn't matter which way you say it. It's Whittaker's Cacao Ghana Intense Dark Chocolate. 92%, but that means it just has 8% space remaining to add sugar. Now, I don't really mind sugar, but I'd rather eat chocolate with more cocoa than sugar. And so this other bar that I got handed has 33% cocoa and has Marlborough sea salt and caramel brittle. I'm going to enjoy eating both, but the 33% cocoa means that it's got an awful lot of other stuff in there, and the first listed ingredient is sugar. So that's what today's seminar is about. It's about what percentage of a wall is made of fluffy insulation when we're trying to meet schedule method. We know we can't keep repeating what we've always done. That would be dumb. So today we're pointing out some changes in design or application that will have remarkable results for your building performance outcomes. I want to encourage those of you planning on coming to the in-person event on the 13th of June to register. That in-person event is our live webinar, which is also live streamed. The registrations are separate on our website, so check which one you're booked for. The stream will finish, and for those in Auckland with us, we will make available a hands-on experience with installing product on our training walls, a decent feed. We have a Mexican food truck booked, and then a professionally hosted quiz night. So let's get started on today's topic, H1 energy efficiency, and a continued discussion on how then should we build. What we know through decades of trial and error is just adding insulation doesn't solve all the world's problems, and that is what Catherine McGregor will present today. I'll introduce her in just a moment. The last sessions we've looked at some minor weather tightness changes that can make a difference to the performance of the construction. We've looked at design choices that dictate durability rather than just treating timber. In 2 weeks' time, we finish up this series with what we've called the naughty child of E3. E3 internal moisture. That's the online and in-person event. Right, during this presentation, we welcome your questions, your comments and objections, and where possible, we will answer these along the way. Please find the chat function and the question tab on your screen. In the chat box, we will post links to you during the presentation. If you have a question, please use the question tab. NZRAB CPD points, 10 points for this presentation that we load for you, 1 LBB point that you can claim yourself through the portal. During the presentation, we have a few poll questions that will be answered by 2 of our nationwide team. We have Simon Cater, based in Auckland, and Ben Ingledew, who is based in Christchurch. We'll bring them in to briefly discuss poll questions, and they'll be available at the end for our Q&A time. Well, Catherine, or Kat, known as Kat. If she's a friend, it's Kat, right? She's based in Chile, Arrowtown, with the lofty title Lower South Island Regional Sales Manager. When Kat is not traveling between Dunedin or Timaru or Gore in her branded Pro Clima car, she goes incognito and rides downhill mountain bikes. She wears a full face helmet to protect that winning smile, and she rides a bespoke Shan N5 set up as a 27.5 mullet. The best bit of data from the bike website is the N5 rides 2 kilometers an hour faster than similar bikes, which is a great connection to our presentation today, where we are going to compare houses with houses, and that's horrendously difficult, but Kat is going to do it anyway. Thankfully, her skill set allows her to do this. The challenge is to make it more useful than that bike data. On that note, I'll hand over to the cold 8-degree Arrowtown Catherine McGregor. Over to you, Kat.
Thanks, John, for that lovely introduction. So let's just crack onto it because we've got a lot of things to cover. So on screen, what you can see is a garage that they have decided to line with Intello for various reasons. Currently storing bales and bales of insulation. The importance of this photo really signifies our topic we are covering today, H1, and what this clause of the code actually relates to. Rightly so, the first thing we think of when we think of H1 is insulation. Clause H1, energy efficiency, describes performance, not material. In fact, the clause doesn't actually use the word insulation. Instead, it describes the efficient use of energy. There are so many variables and things to consider in this clause, I really wonder why we underestimate it. So let's go unpack it. Firstly, the functional requirement says buildings must be constructed to achieve an adequate degree of energy efficiency when that energy is used for modification of temperature, humidity, ventilation, hot water, and lighting. That simply means if you are using energy for anything like heating, air, or water, do it efficiently. So here comes the insulation bit, adequate thermal resistance. The performance requirement says within the building envelope, where the temperature or humidity or both are modified, must be constructed to provide adequate thermal resistance and limit uncontrolled airflow. Let's summarize that right now. Insulation and air tightness go together. H1, done. I think we should all go home. If it were that easy, we would be doing this already, so you can't go home just yet. Of course, there are some complicating factors. Account must be taken of physical conditions likely to affect energy performance of the building, including the thermal mass of building elements, orientation of the building and shape, the air tightness of the building envelope. There it is again, air tightness. Also, lots of things in our houses generate heat, and the code talks about these. Heat gains from services like hot water cylinders, processes like cooking, and even occupants including cats. And I've heard a rumour that you can heat a passive house with 16 cats. I don't know about that, and the local climate, which is what we're going to compare today, and also heat gains from solar radiation, which is related to things like window size and building orientation. So what is it that's wrecking our attempts to have a warm, dry, healthy building? Firstly, let's take some time at design. This picture is a friend's house being renovated in Arrowtown, being built around about the 1990s. We have pink bats inside external timber frame walls, a sheet of ply covering where the window was, and this external wall is connecting to, as shown, an internal wall and a mid-floor. What we uncovered was black mold on a lot of these external walls. The code clause H1 talks about adequate resistance, and this wall did something good during its lifetime to provide resistance to energy flow. However, when it got damp enough to grow black mold, I would suggest it wasn't resisting energy movement adequately. What we know is, unfortunately, new designs are not always better than this 1990s wall. There are a couple of things going on in this image. Moisture is moving through this wall with the energy. Some of the moisture is reaching cool temperatures and condensing. Now, this is connected to E3 more so, but the clauses are all interconnected as we know. H1 provides construction R values that you can now meet for each climate, but is this good enough? What's in my slide title? 1 to 100. This means we take 1 minute in design or application to ensure we get 100 years of performance. The 1 to 100 rule we are applying here is that instead of just following the schedule method, you take a minute to look at your design. Beyond compliance, what about the actual performance on day 1, week 1, month 1, year 1, etc. For this reason alone, we should not be designing to minimums. So speaking of minimums, let's look at the schedule method table. As John and I were discussing the best way to let you know dumb stuff at H1, we kept coming back to the same table. All over the country, the required thermal resistance is the same or very similar. Why? Isn't the North Island way warmer than the Deep South? We looked into that too, and the mean temperature between Auckland and Arrowtown isn't massively different. About 8 degrees different in the middle of winter, according to NIWA data. Down here in Arrowtown, we are colder for longer, and my hot water bottle gets refilled multiple times a day at the moment because the heat pump struggles to get out of bed in the morning. So we decided the best way to show this was to take where we live, so John in Auckland and myself here in Arrowtown, and compare the same schedule method compliant house in different climates and see what the outcome was. And the outcome has to be measured in energy. Yeah, so this is the model that we're going to be talking about. So now things get complicated and in depth really quickly. So I've reduced the level of complexity because we are comparing climate by eliminating things like location shading, as they are vastly different, and chosen R0.5 for the windows, which is double glazing, thermally broken aluminium frame. And we have recessed these windows in line with the insulation. So let me explain why. Why? Because of ice. Just here. I have ice in my house and it's not all in the freezer. It's right here in the photo. It's on the inside of the frame on the left picture on screen. Built in 2017 in Arrowtown, the windows here are non-thermally broken aluminium. They are double glazed, installed to E2 AS1 window details. They might be weather tight, but is sure as heck not thermal anything. The middle image, figure 4, shows a similar window. However, this has been drawn with a thermally broken frame, but it's still hanging outside the wall frame and therefore outside the insulation line. Just staying with that middle image for a moment, there's some tiny red dots and around the aluminium, and these indicate the highest heat loss, which is where we will see condensation first. According to thermal simulations installed like this in figure 4, the middle one, thermally broken frames will only achieve a 1 degree increase in surface temperature at the sill, compared to non-thermally broken frames installed the same way. 1 degree Celsius, that is not a lot. So move the window inside, recess it into the frame line for better performance. That is what is shown on the image on the right-hand side. These images are plucked from an eBOS article co-written by John and Anthony Hopper from Technoform several years ago. If you want to learn more, then hover your camera over the QR code and it will take you direct to Triple Connected Window article, which is one out of the 2 on the same topic. So let's now go into a poll, guys.
Right, thanks, Kat. So those are fun articles to write, by the way, the triple connected windows. And yeah, just trying to look at improvements. And I think we've got a comment in there just about knowing that we can do better than what you had on screen there as well. So I think that was around about the 2017 mark, that article. Right, let's get into our poll question. This is a test of what you've heard so far. What is the dumbest thing we do with good windows? So we've had one of these questions like this all the way through our seminar series so far. What's the dumbest thing we do with a particular thing related to the topic? So let's do that poll. Do you choose the dumbest thing is to forget to open them? And is the dumbest thing that we do install them recessed in the thermal envelope? It's a bit of a double negative on that, isn't it? Is the dumbest thing that we hang them outside the thermal envelope, or is the worst thing that we would drill condensation drains through the frames? So if you'd like to answer that poll question, give you just a few more seconds, and let's go for those. You can see that coming up. What have we got there? Oh, yes. Well, Ben, Simon, shall I hand it over to you guys? And you can maybe have a wee chat about, thankfully, not too many, only 1% of people got tricked by my second question there. Or maybe that's the real answer for that person, I don't know. Right, Ben.
Yeah, well, I thought that putting condensation drains in the frames was a bit crazy, John. Why would we need to be draining water out from our windows? What do you think, Ben?
Well, we do drain water out from the windows because that's what we've got. So that image there with Kat's windows with the ice, you know, that's going to melt. There's water on the glass. It needs to be removed. You either get a towel out, a squeegee, a hand towel, a paper, you know, or let it drain out, right? So is it a bad idea to put drainage holes in your frames?
It's a fantastic idea if you want to let cold air into your house and your heat out. Internal gutters, I think we call them. But I did hear one window association member, who should remain nameless, call it a free dehumidifier. That's what was running there. But yes, the vast majority of people have also agreed that hanging them outside the thermal envelope is the dumbest thing we can do. And that's it's good to know that the education that is going on through the industry is gaining some traction.
Yeah, so comment there. So that was 82% of people said that is the dumbest thing we do. I think the challenge that we have, and we know that the E2AS1 details are acceptable solution 1 details, therefore they are accepted through council every time, and we covered this in the E2 presentation as well, but that is one of the default settings. So yes, we have 82% of people say that it's the dumbest thing to do to hang them outside the thermal envelope, but do we have great other options? And the answer is yes, we do. Are they accepted everywhere by default yet? No. Ben, go for it.
Just briefly, 13% have said we forget to open them, and that is valid. That it doesn't matter how good your window is, if you're not opening them regularly to ventilate, then without mechanical ventilation, we are going to have a big problem. So yeah.
Right. Okay. Well, we better keep moving on. So that QR code still on screen there to the Triple Connected Windows articles, and which are brilliantly written, by the way. Let's move on. Kat, back to you.
So modest. Okay, so based on that poll and the discussions, what I'm going to show when we show the modelling is at the starting point we're going to use recessed windows. So the next thing is to check out the insulation choices we have been forced to make. So in this webinar series, you have now seen this photo on the left for the 3rd time, and you can see we really like to mix things up. But this time we are looking at the conductivity and the proportions of timber versus insulation. As you can see, there's not much room in the photo for the better performing material here. In fact, I'm going to call it 57% framing and 43% insulation space. Why? Well, that's what Beacon Pathways research showed was the worst wool. So worst meaning the highest percentage of timber, therefore the least room for insulation. So on the chart, you will see this is the worst of 57% timber highlighted down the right-hand side as a comparison to normal. Normal is from Beacon Pathways research, which showed an average of almost 35%. Framing also now highlighted on the screen. This is a problem for us because the assumed amount of timber in any clear wall, meaning no windows or any other additional framing, we assumed and calculated with 18% timber. This is a problem. In the chart, right down the center, I've taken 4 different insulation R values. That is what's stamped on the bag, and their thermal conductivity values, meaning how fast the material conducts energy. And so what you see here, the lower the number, the better. And these could be any fluffy insulation material. And we looked at how these actually perform in a wall where 18%, 35%, and 57% timber exists. What does it really show for the 90mm frame in reality? It shows that it's not realistically possible to achieve schedule method value of R2 in a wall with a 90mm frame depth. The problem is not the frame itself, it's the amount of insulation and where the insulation is placed. Remember, we're trying to achieve schedule method numbers here, just the so-called easiest way to comply. The second chart, looking at 140mm frame depth, shows it is possible without any real effort at the average of 35% timber to achieve a construction R value of 2. So let me point out a couple of things. the success in the 2 green boxes here in the top chart are only theoretically possible but aren't real. 18% timber isn't practical. That means 90mm frame can't achieve schedule method R2 on its own. Secondly, the performance of the better quality insulation will come at a cost premium. The cost difference between insulation at R2.6 and 2.8 is close to double, but the performance improvement is just R0.1. However, talk to your insulation suppliers about the most cost-effective way of achieving the required R values. They know and have many different options to offer. So now we get into the modelling method. Here are 2 images in SketchUp that are the same house from different angles. Single level, not radical at all. SketchUp allows all components and the geometry of the building to be established. It's then analysed by a plugin, and then the energy demand is output into a big, ugly spreadsheet. So what have we modelled? We have taken a typical 3-bed, 2-bath building and put it in climate zone 1 in Auckland and climate zone 6 in Queenstown. To attempt to compare apples with apples and let climate show its true impact, the parameters are both lined up direct north to south. Due to location shading being dramatically different and therefore hard to compare sensibly, we omitted that from both. Locational shading can add significantly more energy demand. The model is simplified, i.e. there is minimal thermal bridging. There will be additional demand not accounted for here. Both have R2.2 in wall, both have R2.2 in walls at 140mm. We went slightly above code reference. And why is interesting, and it goes back to the timber versus insulation percent chart. Trying to get a wall exactly schedule method R2.0 was harder than expected. A 90mm frame only worked if we cheated and used just 12% timber, so that's dumb. So of course, we jumped to a 140mm frame. Now we have the opposite problem. Making it bad enough to stay down at R2 required 44% timber frame. So for ease, we used the more realistic 35% timber, and this gave us an R2.2 wall. We've also got R6.6 in the roof, our value in the ceiling, a 0.5 average in windows recessed, an R3 and a suspended floor, and we made the houses climate zone 6 reference for consistency. We did 5 air changes, and windows will be the strategy for getting fresh outdoor air, which is normal and schedule method. All right, enough talk. What's the answer and what happens? So just remembering what I've just described on the previous slide is the reference building on the left of the graph on the screen, with the picture on the right to remind you. So I've named it reference here, as that is exactly what it is. The reference building as modelled, performing in blue, representing Auckland, and in green is the Arrowtown version. The numbers or the units or scale on the left up here is in kilowatt hours per metre squared per annum, from 0 at the bottom to 120 at the top. It is heating demand only. I've deliberately left out cooling demand, even though the Auckland house here is overheating a whole lot. It's still not normal to cool. Heating demand only means I need to turn the heater on to keep the house warmer at a consistent temperature of 20 degrees. The house is a measurable amount of energy per metre squared per annum. For reference to what is a good and a poor performance, about 50 kilowatt hours per square metre per annum is considered a good building. A certified passive house, by comparison, targets less than 15 kilowatt hours per square metre per annum, and anything over 100 is really not good. John's 1939 uninsulated, yet to be renovated home is at 223 kilowatt hours using the same modelling software. And I've modelled several modest new homes in Queenstown Lakes at around 130 to 160 kilowatt hours per square metre per annum. So we need to improve. So let's get into the numbers and the modifications without really changing the materials. The reference building blue in Auckland is sitting at around 33 compared to 112, which is green in Arrowtown. So our cost to heat in Arrowtown is getting close to 4 times higher than Auckland with the same schedule method compliant build. The first change in comparison to the reference building we made was to swap out the 140mm frame to a 90/45 with a 45 internal service cavity. It didn't quite make the impact as expected. So on screen here is showing a 90mm frame with a 45mm service cavity on the right, and the QR codes on screen is to our construction library. So the 90mm frame and 45 is cheaper than the 140mm framing, and it is lighter. There is a higher labour content, but we've saved 4 kilowatt hours per metre squared in Arrowtown and 2 kilowatt hours per metre squared per annum in Auckland. The next change was air tightness only. It was a big reduction in energy demand from the reference building from 33 to 25 in Auckland and from 112 to 91 kilowatt hours per metre squared in Arrowtown. This change is not shown on screen, but it's part of the mechanical heat recovery, ventilation and air change information in a couple of slides. This change was to improve the level of air tightness from 5 air changes per hour down to 1 air change per hour. Now, before you say, here's the sale of Pro Clima air tightness products, let me point out the products you are already designing with are mostly airtight. However, you might not be connecting these together. For example, take this section of the house. There are a number of construction methods in this building. However, all need to be connected and continuous from the floor to the walls, through mid-floors, back to the walls, and then roof. In particular, if you have a concrete floor, it's airtight. Connect that to your OSB internal sheathing and then tape those joins. Plywood is airtight, and all you have to do is tape those joins. Timber sheet flooring is airtight. Tape the joins, connect them all together. It's quite simple that way. With all that in mind, let's go to a poll, John.
Thanks, Kat. Yeah, I was just thinking through that. So the model that you've got there in SketchUp is actually with a sheet timber sheet flooring product as a suspended timber floor. So that is a perfect example of what you just described, which wasn't actually in the list, right? Like that product as, you know, like a strand board floor or even a plywood floor, and you're just saying connect the sheets together because the product is airtight. But there you are selling some Pro Clima products there.
Yeah, just not Intello, you know, even though Ben's got Intello behind him. Like.
That's good. I did see the air tightness membranes in the bottom of the list there. Nice. All right. Okay, well, let's kick into the poll question, and it is around these products. So what are you designing to create air tightness? And we'll make some of the comment about some other options in there as well. So yeah, first answer there is concrete. ICF is your insulated concrete forms. So that's that would be like your, I mean, if you're designing with this, you know, so I'm just describing this for other people, but the insulated concrete form is like the Lego type blocks, great big Lego blocks, but they've got voids through the center where you'd pour concrete. Proprietary air tightness membrane, of course, that's something like Intello, like our air tightness layer, OSB or plywood, as Kat just described, or you've nothing decided. What if I write it like that? Nothing decided yet. So that would be, I'm not yet deliberately detailing, designing, creating, working with air tightness layers yet. So that's plenty of time to answer all of that. Let's kick into the answers. What do we get?
Well, that's good to see.
Yeah, that's pretty good, eh, Ben? Yeah, it seems like a lot of people are keen to use air tightness membranes, but if they were going for ICF, of course, the concrete layer would be giving your air tightness layer. So it'd be really important to consider your connections from the concrete to the windows and other elements of the building.
It's also interesting that you got 20% as saying nothing decided yet, and I think that's very reflective of what the industry is doing, where we're thinking about air tightness. We know we've got to understand it, but we're still trying to figure out the best way to do that in a way that we understand. Of course, the difference between all of these products and the one that's behind me on the wall is the humidity variability, and that variability is so important for managing moisture within the wall.
Cool. So the nothing decided yet. I mean, that's, again, this is what we're trying to point out on this slide, that without necessarily going out and buying, specifying, installing dedicated air tightness membranes, there are products which we already have. Even plasterboard is technically airtight. Of course, the challenge is all of the holes that we poke through those products for PowerPoint light switches and the fact that they don't generally seal to other products. Well, actually, that's not entirely true. Jib Sound Seal is an entire acoustic system that is a dedicated system of preventing flanking noise around the product. So there are some options there. Anything else on that? We haven't talked about windows or skylights taped there, which is the fourth one down.
It's so important.
Well, of course, yeah. So, Kat, do you want to hit that? So, what is the importance of that? I mean, if you just use the image which is on screen there, you talked about floors, walls, ceilings.
Yeah, windows are a bit of a hole in our thermal envelope, right? So it's quite important to get those really taped up, either just from the inside or from the inside and the outside.
Cool. Okay. So yeah, inside definitely, outside depending on the type of window frame, because that becomes a water drainage issue potentially as well. That's good. Okay, good. That was, yeah. Anything else on that? I know straw bale is there, but really it's not about the straw bale being airtight. It's about the coatings, the screed, the plaster, the renders over that. Right, Ben, you got your hand up quickly.
However, I've been in the straw bale houses. They're awesome. They feel so nice to be inside.
Got a very different feel to them. A short story about a site I visited recently where an architect had designed a house to be airtight, less than 3.5 air changes was their target, and they just made an assumption that you don't really have to plan that in, and houses are getting more and more airtight anyway. I went round to the site because the builder was fraught because he'd done a blower door test and he'd got air changes around 5, and he was going around with foam spraying into flush boxes, trying to eliminate the air leakage. And this is just what we have to try and avoid in the industry, is making all these assumptions and not planning for it, and then having to run around with some drastic measure that, I mean, I was very doubtful that was acceptable to any electrician. But yeah, that's the horror story we need to avoid.
Yeah, cool.
So another one there, John.
Simon,
yeah, just considering mass timber. Sometimes it's assumed that mass timber would be airtight, but it's always good to make sure that you actually check that with the manufacturer. In some cases, you would need to use some type of an air tightness layer, which could be the peel and stick membrane on the outside. Especially if you're going to insulate on the outside of that, you can use your air tightness layer, always remembering to keep air tightness on the inside of the insulation.
Okay, hey, thanks for that. That's good. I'm just going to do one more thing before you guys disappear. One of the questions which has come in, and Ben, you did answer this, but I'm just going to get you to kind of repeat. But let me ask the question. It is, why did you assume 5 air changes per hour? So I'll couch that question better. Kat, you talked about 5 air changes per hour in the model that you've put in for Arrowtown and Auckland. The question that we've had come in as, why did you assume 5 air changes per hour? So Ben, you've kind of answered it, but I mean, do we need to cover more of that? Almost answered already, right?
Almost.
I think,
5 air changes is pretty common, right? It's kind of in the middle between about 3 and 7. It does fluctuate quite a lot, you know, so I think 5 air changes is a really happy medium.
Yeah, okay.
A modern new build house, following good practice would come in, like Kat says, between 3 and 7 air changes without having to tape anything. But it's not a given. It's not. You certainly can't assume that just by doing a job well you're going to get 3. It's still got to be well thought out. American standard is 5. Australian standard is, I believe, 10. So Danish standard is 0.5.
Yeah, can I point out there that the Australian standard is a target. We have no target. So even though their target is 10, and that's quite drafty, quite air leaky, at least they have a target. We have none. Hey, we're going to move on. Thanks, guys. Kat, we'll hand back to you to carry on.
Okay, sweet. Right, let's go back to the graph data and look at the effects of air tightness. So, same graph, same rules. In the third column here, we have now added mechanical ventilation with heat recovery and changed our air tightness value from 5 to 1. Those are two related but different things in this building. Remember, the initial model was normal construction where 5 air changes per hour of air leakage is to be expected. We changed that to 1 air change per hour. So that's a deliberate air tightness. Sealing up sheet joints, sealing pipe penetrations, eliminating downlights, penetrating the otherwise airtight plasterboard layer. However, houses that are deliberately airtight need ventilation. What we've added in the model is not just airflow, we've added airflow in and out of the building with a balanced heat recovery unit. However, this one has a cost. So what is the energy difference? We're not bleeding out of the building we're not bleeding energy out of the building when it's windy, and we're recovering the heat the occupant has already paid for through the ventilation system. So we went from 112 kilowatt hours meter squared per annum, and we dropped to 69 kilowatt hours in Arrowtown. Auckland at this point is a bit of a lemon in our comparison, because due to the decision to not model the shading from the location, you know, from overhangs and trees, etc., we've got a lot of overheating going on. And a reminder from this modelling, it's showing the scale of change, not the fact it looks like we've accidentally got close to passive house level of performance in Auckland. The Arrowtown house was also experiencing temperature fluctuations due to lack of shading. So take the overall message of improvement here. So if we're sticking with the Arrowtown house in the green, after creating air tightness to air change to 1 air change per hour, we dropped to 91. And then including mechanical ventilation with heat recovery, and with all the 3 changes combined, including the 90-45 mil frame, it gave us 65 kilowatt hours per metre squared in Arrowtown. That's almost halving the energy demand. So that's a schedule method improved house in Auckland and Arrowtown. A final comment, while I've added the cost of a ventilation system, it's not just about reducing energy demand. It's also about comfort and health for occupants at a reasonable running cost. It also gives an indication of the weirdness of having the same R values required in all areas of the country for ceilings and walls. And this chart nails the whole point, which is the same house needs something other than schedule method in different climates. So, you know, use the modelling method instead. So, you know, what do we do now? What we've looked at, well, we have used values from the schedule method and modelled what the outcome will actually be using the passive house planning package. this modelling method isn't reserved for passive houses. It is a useful tool that you can use for any building. So, choose your method of calculation wisely. Don't just accept schedule, as you will be paying for it one way or the other. Using the modelling method allows you to predict energy demand in the climate you are designing for. Neither schedule method or calculation method give you this information about that energy demand. It also allows you to tweak the design during design to reach the target you or your client set. If you state that 50 kilowatt hours per metre squared per annum is the worst you will design to, I will predict you'll end up with happy customers. So, let me give you a nudge towards other elements of better design. You may be familiar with the 5 principles of passive house. You don't need to be aiming at certified passive houses, but to get your energy demand down, you do need to look at these 5 things. So starting bottom left, thermal insulation, I think we've covered enough. Windows, have the view, but check your windows. Make sure they're recessed. External shading, size and solar gain, the solar gains through the glass. Ventilation. Ventilation is not infiltration. Proper ventilation is important. Air tightness. So air tightness is getting the full construction R value that is available. And lastly, thermal bridging. Thermal bridge reduction removes those horrible cold spots around the perimeter of a building. So now I've given you a heads up on the insulation and heating demand. We slightly touched on getting good windows working to prevent heat loss. It can seem a bit of a head scratcher, but it's not all doom and gloom for those of you who want to put in huge expanses of glazing or views for days. This picture is called a window wall. Actually, it works with this house. It's a certified passive house that was modelled, and having these windows here would have meant that other areas of this house had to perform better to make up for it. These windows are very high performing, suited for helping prevent this house overheat, which is something I really want to mention. Overheating. This is important and we don't really consider this. The sun is seen as free heat and is a form of heating our house. Solar gain is so nice, in fact, that I'm writing this in front of my window to be warm. Cooling can be just as annoying to control as heating and as expensive. So opt for external shading first, as you can see in this picture, with a large overhang to support those windows. Plant those trees, put those pergolas in. Also look for good window glazing and look at your window frames. And most importantly, keep the building airtight, as it helps with cooling as well as heating. So that's me.
Right.
John?
Thanks, Kat.
Yeah,
great. Hey, we've got a really good question around it was much earlier in the presentation, but around the conductivity and the R value. So great, Ben and Simon are on. So what is the difference between the conductivity and the R value? Who would like to, in fact, Kat, do you want to answer that? Yeah, great.
The thermal conductivity of a material is its ability to conduct heat on its own. When you introduce an R value, that needs the thermal conductivity value and thickness of the material. So it's not just, it's not just the thermal conductivity. An R value is thickness divided by thermal conductivity, and that gives you your answer there.
Okay, that's a fairly technical response to that. Maybe Ben, do you want to? I mean, that's right. So, and I'm not mocking. It's a.
It's the right answer, and I would just add to it that the R value is the resistance because of the depth of the material. Just like you said, Kat, it's got a certain thermal conductivity, and because of the depth of it, it has a resistance. So it's like, and then the U value is the flow rate, as in how much the energy is flowing through there. So they are the opposites, they're the inverse, the opposites of each other, just like Kat said, which is why you do the clever mathsy stuff with the 1/whatchamacallits and Yeah, very good. I didn't get that, but I understand. I know you know.
I know you know.
That's
that
the
I know.
important
That you know.
bit. Yeah. Is that clear, John? Oh,
You're
you lost your
muted,
mic there, John.
Lost.
Oh,
It's
sorry,
okay.
sorry, team.
Probably for the best.
Okay, is that clear? I wasn't listening. I was looking at this next question, which is a really good one, and it's a bit of a toughie actually. So, 65 kilowatts per square meter, kilowatt hours per square meter per annum. That's not great. Full stop. So, Kat, I'm not going to throw that to you. Ben, maybe do you want to just hit that one, please? Because it's a good point.
Yes. It depends what your standard is, isn't it? But 65 kilowatts. Yeah, it's not that great compared to say a passive house standard. But this was the modelled scheduled methods with improvements. I think you missed the point there slightly, that we're looking at the improvements that can be made by introducing one or two factors. Simon, what do you think? What do you think about that?
Yeah. No, I agree totally. I mean, 65 is, let's put it this way, it's a lot better than what we had with the old H1. I don't know, I heard people talking somewhere around 120 kilowatt hours. So, 65 is certainly improving things, but I would think if you want going to be down in Arrowtown, Queenstown, you'd want something a lot better than that. And another point that we were just discussing earlier was around the fact that along with the air tightness, we've considered the ventilation. And yes, we are adding something in there, which is a ventilation system. But I think it's a key element, because currently we're relying on our openable window space to ventilate our buildings. And I was just having a chat with Cora Rosemeyer the other day, and she was explaining to me the lack of performance that we're getting out of our openable window space to actually do a good job of creating good ventilation.
Hey, that's really good. Simon, I'm just going to jump in there. Kat, do you want to keep responding to that, and then I'll jump in
just
with
really quickly before that goes away. Adding air tightness or ventilation gave a similar result. When you add them both together, that's where it makes a difference. That's quite a key.
Right.
Yes, because you went from 112 kilowatts. You added air tightness.
Yeah.
Sorry, so it's 112 down to 91 when you added air tightness, but it dropped to 69 when you also included the heat recovery ventilation, which, so the question that I had, you said using the same materials, yet you added a ventilation system, windows question mark. So and Simon, you've really covered that. So it was one of these things that we anticipated, and I think we even advertised. Is that false advertising? That we advertised this idea of changes with your pencil can make some really significant improvements. Well, yes, they can, but ventilation and air tightness do go well together. All right, let's jump into a couple of questions to you, Kat. One of them is, I've moved it. What is the plugin for SketchUp that gets those thermal results and calculations? So your modeling was the red, the red homes that is in SketchUp. Then what do you do with it?
Well, you can put it straight into Passive House Planning Package, which is that massive spreadsheet. However, I use Design PH, and it's very helpful, because when you go back from the model to Design PH, you can everything's all highlighted. You can make things have names and go through all the windows correctly, and it's quite an amazing tool. It's quite tricky until you get your head around it, but it's very, very helpful.
Cool. Okay, just to clarify, it's called Design PH, and it's a plugin in SketchUp, and then that moves, basically it strips the data out of that model and moves that directly into the spreadsheet.
Yep. Okay. And it's actually very cool.
All right. Well, actually, the next question.
Energy nerds, Kat.
Pardon?
I say cool for energy nerds like you.
Oh, yeah. Yeah.
Sorry, John.
Nice. Yeah. Okay. So next question then is on that. So where did I put that? Well, I think what is the cost to get a thermal model done for an average-sized house, and what software can you use to do modeling? So we could probably, let's split that. Let's do the first one first. So what is the cost to get a thermal model done for an average-sized house?
It depends. It depends what you want out of it. I think it can range anywhere from, you know, a couple of grand all the way up to, you know, if you're getting something really, really thoroughly done, up to, you know, 8 to 10 grand.
Okay.
So about maybe about 1,500 to about 10 grand. I know it's quite a lot, but if you're going like, say, certified passive house, that's when you're up 8 grand-ish, right? If you're just getting things for a normal house, around about 2,000.
Seems a little bit bit of a stab in the dark there. Bit of a stab in the dark there, Kat.
No,
Maybe,
there's so many like things to consider in that question.
Yep, that's a toughie.
Yeah.
It's a bit like saying, how much does it cost to build a house, John? It's sort of, you know, it's such an open answer. It all depends on what you're trying to achieve and the complexity. But the question was about an average house, so
An average house, yeah.
we're talking the bottom end.
Cool.
John,
Okay,
1,500 to about 2,000 for a very simple.
I was actually chatting to someone who is an energy modeler who was saying he can do it for under a grand. So I think
Oh, yeah.
certainly on the way down.
Well, I mean, and we're not trying to, you know, find the cheapest. We're trying to get to the best. But I do know that if we answer the second part of that question, which was what energy models can you use the passive house planning package for H1 compliance. You can use Echo as well. What else can you use? I think what was the one that
New Zealand Green Building Council has something, don't they?
Was it?
Yeah,
How about if there's any energy modelers listening, they can put a quick quote in the questions and then we can check them will work. That's the good.
Okay, I'm going to move to a new question. So yeah, adding the price, because we've covered this one, but adding the price of the MVHR, the cost or the missing out that step, I think I'm sort of interpreting this question, will be the damage to the building because you didn't ventilate it properly. Well, yes. I mean, I think the answer there, answer is you need to ventilate, and we haven't even got that in our code clause combo. We didn't add G4 ventilation as a full discussion, but Ben, I think you will be discussing this in 2 weeks' time in your presentation on E3 internal moisture. So we'll probably get back to that.
Moisture.
Okay. All right. Question. Simon, what type and make of heat recovery ventilation systems would you recommend? Well, how about we just simplify that question? What type? So not what brand of heat recovery, but what type, if there are different types.
Well, personally in my house, I've got a centralized ducted heat recovery system. So effectively you've got your unit, it's ducted, taking away all the moisture out of your wet areas, and you're supplying fresh air back into your living areas and bedrooms. So it's a ducted heat recovery ventilation system.
Do you want to give us the flip of that? What's the decentralized, just a quick?
Yeah, so your decentralized would basically be something where you've got a unit sitting, which is a through the wall unit, and effectively you would put a number of these into a house. You might have 5 or 6 or whatever is designed, and that will be basically communicating with each other, and it'll be drawing air in, sucking air out, and it uses a ceramic disc to basically store the energy and recover it. But that's a decentralized system as compared to a centralized ducted system.
Cool. Okay. Thanks, Simon. Now we've got a couple of statements there, which are kind of lots of question marks, bit of drama around Kat's answer on the cost of energy modelling. What I
I'm so sorry.
Never
I should have
never
answered it.
It costs.
okay. What I'd like to point out there is that the other option that you have is to not model, and if you don't model, then the outcome is you don't know. And that's what, Kat, you pointed that out in the presentation. You talked about schedule method and calculation method. You don't actually know what the energy demand of that building will be. Well, why do we need to know what that energy demand will be? Ben, let me give that to you as a question. Why is it useful to know what the demand is?
If you don't know what the fuel economy of your car is, you don't know whether you're going to be able to service your car correctly. It's the same with the house. If you don't know the energy demand of your home that you're building, how do you know whether you can actually keep it warm or not? And this is, it might be okay if you've a millionaire. I spoke to somebody in the joinery industry yesterday spending $700,000 on joinery in their home. $700,000. So they obviously don't care on the heat and demand. I know. But for most of us mere mortals, if we don't know the energy demand of our home, then how can we know if we can afford to run it or not? It's okay for the bank to lend us the money, but if we can't service it.
Okay, let me jump into the next question then. Thank you for your presentation. Do you see things improving in the industry, and what would be your target in terms of kilowatt hours per square meter per annum for residential buildings for good design? I'm going to ask all of us, I'll do this too, what is your number? So that's going to be your question. What is the target in terms of kilowatt hours per square meter per annum? Given that, Kat, you're Arrowtown, should this make any difference where we are? Should the target be the same? Simon, Auckland, Ben, Christchurch, me in Auckland. Let me throw it to Kat. What do you think is a good number to sit at? And it's if you weren't building to passive house, so what's an acceptable number to you if you were designing?
Oh man.
Quick.
Okay,
Kat says 50. Right, Simon, what's your answer?
Look, 15 would be awesome, but if you can't meet 15, then I think 30 is something that we could aim for as a sort of an interim means.
Yeah.
Yeah.
Ben?
Definitely. 15 is because it's a passive house standard. That would be my optimum. Wonderful. Why not if we can do it? But it's got to be affordable. Whatever that number is, has got to be affordable to the person who's living in it. If it's not, then there's going to be health concerns. So what's my affordable? Well, I'd like it to be as low as possible. So I've got more disposable income to do the things I enjoy doing. 15.
I think 15. I think mine would be between 30 and 50, and it really depends on your budget of where you want to get to and what climate and how easy it is. Like if you saw how easy it was to improve Auckland, you might be able to get to a better number on less of a budget. However, if you're in a colder climate or more fluctual it might be a little bit harder, and therefore aiming for a good building is a really good idea. Around 50.
Okay, we're gonna hold there. I'm going to ask this last question, which is a bit of a lowball question for you, Kat. Thermomass concrete walls, or the mass in concrete walls, increases the construction R value, but unfortunately isn't considered by H1. I'd beg to differ on that. How can you analyze, or let me ask it, Kat, can you analyze accurately the thermal performance of a thermomass building?
I haven't done it.
Can you?
Well,
Can it be done?
Into the data. Put that data of the concrete into the PHPP.
Cool.
All
right.
Yes.
Hey, great. So I think the answer is yes. It's a bit of a low ball. Yep.
Just costs a bit more.
All right. Hey, thanks, team. And look, on screen, we've got information about our final of the seminar series, which is with Ben, who's on screen with us today. So he is leading that. He's going to be here with us in Auckland as a live event. So that is examining E3, I call it infernal moisture, and we're going to ask the question again, why does my 6-year-old house have condensation on the frames? We just don't need to be cold and mouldy. So today I'd like to thank you for attending, and also our panelists Ben and Simon, and our presenter Catherine McGregor. Please feel free to get hold of any of our team for in-house presentations and on-site assistance. Thanks for attending, and we'll see you next time.
Bye.
Bye.
Bye then.